Okay, so in this video we're going to look at the integral test, and as the name implies, we are going to need integrals in order to evaluate them. So let's look at an example. Say we're trying to decide if this series right here converges or diverges. First of all, let's realize that it's not obviously divergent, because if I try to evaluate the limit as n goes to infinity, 1 over 1 plus n squared, we do get 0. So no use there. The divergence test doesn't help. So we might then try to do like partial sums or something, but of course that's not always accurate. So maybe that's not going to help us, and this is not geometric, right? I hope we all see that this is not a geometric series. So we need some new techniques, and so herein lies the integral test. So what the integral test says is, okay, if I were to write out the terms of this series, remember that the terms themselves would equate to like this point right here is like the value when maybe x is 1, and maybe when x is, I don't know what the scale is here. So let's just pretend this isn't going to be very good, because this might be at a half, and then at 2 this might be a fifth. So this is not drawn to scale. I would say that probably like over here is 1. But just to give you the idea of what's happening is like we just have these finite values along the way along the curve. And we would have to add up all those values. So I'd be like adding up this length plus this length plus this length, because all of these are just telling me the height. Okay, so if I were to add up all those lengths, first of all, just realize that the result here, this is going to be a length, and in other words, it's going to be some number. It's going to be a one-dimensional result, right? It's like the length of a line segment. If I just sort of take all these pieces and stack them on top of each other, I'd get some one number, a length, right? I'm looking for a sum. Versus an integral is certainly not, right? An integral is giving us a two-dimensional area. But even though they're totally different dimensions, I think it is reasonable to see that if the lengths of these segments add up to some finite sum, no, let me say that the other way. Sorry. If this area adds up to some finite sum, right, that the improper integral actually converges. So if the area converges, then it seems safe to assume, it seems like a good correlation. That seems obvious that the sums of just these finite one-dimensional segments would also converge. So if the area converges, then the sum of the terms in the series converge. So now I certainly did not at all prove that to you, and I'm not sure that this visual convinces you either, but it is in fact the case that what the integral test says is in fact just this. So first of all, it says, so say you have some sequence with positive terms. So we are going to stick with positive terms, because if the terms go into the negative, it's not necessarily going to apply. So if the sequence is positive terms, like the one we just looked at, and the function is, so if we wrote, so note this statement right here is saying like, okay, let's temporarily pretend that we have a sequence, but we're going to set it equal to some function that corresponds to it, because in a second we're going to have to integrate that function. So we want to sort of change notations to really think of it as a function. So if this function is positive, decreasing, and the decreasing is sort of like obvious, because if it wasn't decreasing, then we would use the divergence test and get divergence anyway. But so if we have positive, decreasing, and of course continuous, right? So again, this is this statement right here. We're forcing the sequence to become a function that's continuous on some interval from n to infinity. Then what this integral test says is that the series will converge if the improper integral converges, but also that the series will diverge if the improper integral diverges. So they both behave the same way. If they either both converge or they both diverge. So if you can determine whether the improper integral converges or diverges, then you can know whether the series converges or diverges. If it does converge, we don't know what it converges to. So unlike the geometric series test, all we're really finding out here is, does it converge or not? We're not going to be able to answer the question of what does it converge to. Okay, so let's try some integral tests. Of course, make sure always when you're about to apply a test, you have to make sure it applies. So you have to think about this. First of all, notice that the divergence test doesn't help us, because the limit as n goes to infinity of this explicit formula, that would go to 0. So divergence test doesn't help us. It's not geometric, but we do have, if I thought about this as a function, so if I thought of this as x over x squared plus 1, the function is continuous, it is decreasing, and the terms are positive. So what I'm going to do is I'm going to look at the integral from 1 to infinity of this function, and I'm going to decide if this improper integral converges or not. So what I'd like you to do right now, because improper integrals, this should be a review. What I'd ideally like you to do is to pause the video and to work through this and see if you can actually identify whether this converges or not. Remember that the first step requires you to set up a limit, because if you do not set up a limit and you don't make this upper bound be a real value, you are not allowed to apply the fundamental theorem of calculus. There were some of you on the last exam who were trying to get around this by like taking the antiderivative and then at the end taking a limit. That's not allowed. The bottom line is you can't take the antiderivative of this expression if you don't first set up a limit. Okay, so we are going to need a substitution here. And when we go to write everything in terms of this substitution, we get, so this is what we get. And notice that my upper bound is now b squared plus 1, my lower bound is 2, and that's because I had to actually use this expression here to convert my bounds from x to u. And I'm just left with the 1/2 du is my x dx, and the 1 over x squared plus 1 is 1 over u. Okay, now we can apply the fundamental theorem of calculus. And we substitute in our upper bound minus our lower bound, and we now evaluate what happens as b gets infinitely large. Well, then this whole thing is going to go to infinity minus some constant. So we get that this improper integral diverges. Now that tells us by the integral test, so by the integral test, this tells us that the original series also diverges. Let's look at this next example, which actually was the same as that picture I gave you earlier with the graph. So we wrote out these terms. So again, I'm going to think about the function f of x equals 1 over x squared plus 1, and note that, first of all, the terms go to 0, so I'm not going to have a divergence test here, and this is not geometric. So I want to apply the integral test, and I can because these terms are all positive, this function is continuous, and the terms are decreasing. So I look at the improper integral, and I use limits, of course, to evaluate this. So again, I would encourage you to go ahead and pause this and evaluate this improper integral. So we apply the fundamental theorem of calculus, and we see that this improper integral converges to pi over 4. Now, that tells us that the series 1 over n squared plus 1, that converges by the integral test, but not to pi over 4. Okay, remember that what we just found, this value, this pi over 4 right here, this is an area. That is that two-dimensional area that we found. The sum, this is a one-dimensional value, right? We just talked about this in that other picture we had. So we know the integral test tells them they both converge, but I don't know what it converges to. All I know is that the series converges. Okay, let's look at this next one. You might find it helpful if you want to write this as 1 over e to the n power so that it has a positive exponent. If you write it like this, you are more likely to notice that this is in fact exponential. So this is actually a geometric series. If you didn't happen to notice this, by the way, the integral test will absolutely work. But if you did notice it, then you'll save yourself a little time because you can actually just see that the base is just 1 over e. And the first term is when n equals 1, I'm also getting 1 over e. So 1 over e is less than 1. The series converges by the geometric series test, and it converges to a over 1 minus r. So I can think of that as 1 over e over e minus 1 over e. So e minus 1 over e to get a common denominator. So 1 over e times e over e minus 1. So this series converges to 1 over e minus 1. So the bonus by me recognizing that it's geometric is I know that it converges, but I also know what it converges to. If I didn't do that and I did the integral test, I could show that it's convergent, and I would recommend maybe as an extra exercise, you could do this by the integral test you'll get a convergent value, but it will be different than 1 over e minus 1, because remember, this will be finding a two-dimensional area. This is a one-dimensional sum. These two things have totally different units. You can't compare them, but you would know that this converges and would therefore know that the series, you would know that the integral converges, which would tell you that this converges. Okay, let's look at this next example. Go through the usual test. The divergence test won't help us, because notice that these terms, if I look at the limit as n goes to infinity of 2 over 3n plus 5, I'm going to get 0. So that doesn't help me. This is not geometric. So I am going to go ahead and try to apply the integral test. So if I look at the function 2 over 3x plus 5, let's note that the terms are positive. This function is decreasing and the function is continuous. So I can go ahead and apply the integral test. To do that, I'm going to be evaluating the improper integral of the function 2 over 3x plus 5. So again, pause the video and work through this improper integral. To find the antiderivative of this function, you may have done a substitution, but you could have also just kept the 2 up front. And then notice that in the denominator we have like a u, so the antiderivative is going to be natural log of that expression, but we're going to have to multiply by 1/3 or divide by 3 over here in order to undo the chain rule here. So, or do a substitution. Either way, when you evaluate the limit as b goes to infinity, we're going to get infinity. So this series diverges by the integral test. Okay, looking at this last example, they're sort of requiring us to write this as in sigma notation. So you have to note that if you start at 2 and go to infinity, the pattern would be natural log of n over n. Okay, so in this example, first of all, we could think about trying to apply the divergence test, because at first glance it's not clear what's going to happen. We're getting something of the form infinity over infinity. So we could apply L'Hopital's rule. But unfortunately, after all that work, we just get 0 anyway. So the divergence test, it's not going to help us with anything. So we're back to the drawing board. We start from scratch again and we realize, okay, divergence test doesn't help. This is not geometric, so we're going to have to do improper integrals again. Okay, so we're going to look at the improper integral from 2 to infinity of natural log of x over x. And I know I can apply the integral test because I've got positive, decreasing, continuous function. Okay, so yet again, let's pause the video and work through this integral. We set up the limit, and then to evaluate, we're going to do substitution. With my substitution, remember to change your bound. So the lower bound is now natural log of 2. The upper bound is natural log of b. When I evaluate when I substitute, I get natural log of x. All of that is just u, and then the 1 over x dx is just du. Now I integrate. Okay, and then we apply the fundamental theorem of calculus, and yet again we get an infinite result, which tells us that this series diverges by the integral test. Now we're going to, on Friday, we will work through this p-series exploration, which requires the integral test. So please make sure that you understand this. If you have any questions about this video, you ask me so that you're ready to move on Friday.